Okay, so for this first reaction in question 2, we take a look and we have a ketone. We have a strong base. There are protons on the alpha carbons. In this case, all the protons in the alpha carbons are equivalent, so we're going to pull off a proton from that carbon, form the anion. The anion will then attack the electrophilic carbon of the aldehyde. Electrons get protoned up. We initially have an alkoxide anion, and it simply pulls off a proton, and in the end we get an aldol addition product. Simple as that. What happens in this next reaction is simply a electrophilic aromatic substitution reaction, and we get a chlorine. A couple of you thought this reaction wouldn't go because it's deactivated. It is in fact deactivated, but remember the effective electrophile in this case is a chloronium cation. That is a positively charged chlorine. It's a very strong electrophile. Most of the time when you see a single chlorine, it's a chloride, an anion. So it's lost 2 electrons. It's very unhappy. It only has 6 electrons on its valence shell. It's desperate to get some electrons, so it's a very powerful electrophile. The next question was simply trying to do an alkylation reaction, and we have to look at this thing, and that's an ortho-para director, so we get our alkylation in the para position. We really would get very little of the ortho product simply because that isopropyl group is pretty big. This group is pretty big. There'd be a lot of steric interactions between these two groups if it tried to attack in the ortho position. So attack occurs mostly at the para position. Oops. 2D. A couple of things here. Hopefully we realize that we have diethylmalonate. We have very acidic protons here because there's an electron withdrawing group on each side of that methylene group. We have a base, ethoxide. What's it going to do? It can act as a nucleophile. If it acts as a nucleophile and attacks the carbonyl group, it's just going to be reversible. It's not going to lead anywhere. We're going to get back to here. So if it happens to do that, it's just going to come back, and we can pull a proton off, form our anion there. That becomes our nucleophile. We just undergo an SN2 reaction here, and then we have our boom, 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 where we do a decarboxylation of the acid that forms after base-induced hydrolysis. Hopefully some of you simply remember that the diethylmalonate reaction is a synthetic equivalent of kind of the enolate anion of a carboxylic acid, which couldn't form. But there's our new carbon-carbon bond. There's the phenyl group, and there's the CH2 group. The final reaction is simply a Diels-Alder reaction, and you just have to realize that you're going to form a bond between this carbon and this carbon, this carbon and this carbon, and we're making a cyclohexenol ring. And here we go. There it is right there. And that's our final product.